So in order to look at correlation, we're going to have two columns of data, and we're going to do stat, calc, and use regression, simple linear. So the directions are here on the right side. We're going to use stat, regression, simple linear, and then this is going to appear. And we pick our two variables. Our x variable is our explanatory variable, and our y variable is our response variable. And again, our explanatory variable is the one that we think can predict the response. So what does our output look like? We're going to get a lot of information in the output about dependent and independent variable and some other things we're going to be looking at later. But for this section, we're just looking for the correlation coefficient. So we're just looking here for what is R. And here R is 0.49, so it's a moderate correlation, about halfway between 0 and 1. We also know it's positive because it's a positive number. If you click on the arrow on the bottom of that output, you'll see a picture of the data with a line that shows you a positive correlation. We'll talk a little bit about that line in the next class when we look at regression. Oops, didn't mean that. Now, how do we know whether or not the correlation is good enough? Is 0.49 good enough? What correlation are we looking for? Well, we have a chart that is for the correlation coefficient. In the right column is a sample size. And then in the next column, we have alpha is 0.05. And the next one, alpha is 0.01. So a problem will tell you, I'd like you to use the alpha is 0.05 correlation most of the time. We're going to determine the number of pairs of data in the sample, or the sample size n. We're going to identify alpha from the question, how significant do we want it to be? And we find the critical value in the table. And if our correlation is significant, then ignoring the sign, we want to make sure our correlation is greater than what's required for that sample. And then we can interpret whether or not it's sufficient. So I've set up an example for you. Sorry. So I've set up an example for you in StatCrunch called the mother-daughter height. We're going to look at a study to determine the correlation between adult mother and daughter heights to see if there's a correlation. So this data is going to be found on StatCrunch in the group for spring 2020. And it looks like this, so you can find it. So what are the two variables we're going to be looking at? Well, let me grab that data to show you. So here's the data. It says mother and daughter and the heights in inches. So we have two variables, mother and daughter. So going back to our PowerPoint, the two variables are mother and daughter. And what we think is that the mother data, will predict the daughter data. So the mother's height in inches predicts the daughter height in inches. So our explanatory variable is mother and our response variable is daughter. So we're going to use StatCrunch to determine the correlation coefficient, and we have a sample of 25 data values in our sample, and we're going to use alpha equals 0.05. So if we look at this data chart for the critical values, we have 25 has a critical value of 0.396. This is our critical value. So we need our correlation coefficient R to be larger. And when we say larger, we mean ignoring the sign. So if we have a negative 0.8, that would be fine. We're ignoring that negative sign and trying to make sure it's going to be greater than 0.396. So this is how we find the regression. I'm going to come back to this in a second. I'm going to show you live how we do that. So here we are in StatCrunch, and we do stat because we're trying to do a calculation, and we're going to go down to regression and simple linear. So there's other kinds of regression, but in this course we look at simple linear. And it asks you about the X variable and the Y variable. The rest of this, the hypothesis tests and et cetera, we don't cover in this class. So we just want to know our X variable, which is our explanatory variable, mother, and our Y variable is our daughter, our response variable, and we click compute. So it really is quite simple as long as you remember the regression. Okay, let me bring my results over. There's a lot of results we're going to get here that we'll talk about later, but at this point we're only looking for the results to get the R, or the correlation coefficient. In this case, we get R equals negative 0.255. Generally, you'll see this rounded to 3 decimal places. So it was negative 2.2549, so I'm going to round to 0.255. So that's quite a weak correlation coefficient because it's much closer to 0 than it is to negative 1. It's also a negative correlation coefficient, so we're talking about a picture of data going downhill like that. So going back to our PowerPoint, we have negative 0.254, and we compare that value of R to 0.396. Because R is less than 0.396, the data is not showing a significant linear correlation. So we say we don't really have a correlation at this point using this data. Now, as you notice, if you look at those critical values, then the higher the sample size, the lower the critical value you need. So it may be worth it to get more data. So for example, if you had only 8 data values, you need a 0.707. With 18, you need 0.468. So instead of having 25, if we had 50 or 100 data values, we may actually have a correlation that is worth it, that's significant. The last part of this section is to look at correlation and causation. Now, an important part of statistics is to realize that correlation says those variables go together, but it doesn't say that one causes another, even if we think that may be true. It's not a cause and effect relationship between the variables. So our question, does X cause Y? Does Y cause X? Could it be some third variable, or is this just a coincidence? So let's look at some of these examples. Does X cause Y? For example, correlation between hours in the tutoring center and GPA. Does spending more time in the tutoring center lead to a higher GPA? Perhaps. If you're getting more tutoring, you're going to get higher grades. But maybe Y causes X. Maybe the correlation between hours in the tutoring center and GPA is because students who have a higher GPA tend to spend time in the tutoring center. They tend to get more help because they have a much more emphasis on their GPA. Could a relationship between two variables be caused by a third variable or a combination of several variables? Possibly. For example, there is a high correlation between the number of shark attacks on Cape Cod, and it's highly correlated to the amount of ice cream sales. Now, do shark attacks cause ice cream sales? Do ice cream sales cause shark attacks? No, both ice cream sales and shark attacks are correlated to the temperature of the air and water. So when the temperature is higher in the air and water, people tend to be in the water, and so do sharks. Or maybe there's a coincidence. There's a strong correlation between the number of animal species in certain regions and the number of people who have more than 2 cars in those regions. There's really no reasonable explanation for some sort of cause and effect relationship. Animals don't cause people to have more cars, and cars don't cause people to have more species of animals.